So, computer project 3. Just the recollection, the first computer project was really just about an integration approach, high order, to look at chaos and sensitivity. The second one was for you to build up sort of a basic solver of one differential equation, you don't need to find analytical solution. You can just try, just to remember that. So I think it's a good thing to try, get some insight while we do numerical methods. The third project is probably, I think, the hardest one, because now you're going to take your sort of basic PDE and transform it into a spatial marching laminar boundary layer code. And I'm going to talk a lot about that today. I should also get out my own personal notes on it, so this goes easier. And obviously involves a little bit more effort, but it uses the Crank-Nicolson scheme and the same type of linear algebra solver. But now there's two PDEs, one which is continuity and one is for the x-momentum equation. And you'll see the fourth computer project actually implementing the Baldwin-Lomax turbulence model, which we'll talk about in a week, is extremely easy. It's just adding one more term to the equations, which is a Reynolds stress term. And the other good thing about this laminar flow solver is that it should also correspond to the solutions of Boussinesq, which we showed a third order differential equation in class. So it's easy to just type that into MATLAB and get a numerical solution you can directly compare. So all that's possible and more. So this is the first page of the class handout, and let's just go through it together. And then after that, I'd like to talk about some more equations which maybe aren't on here that might help you, and I'll talk about how I wrote my version of the program. So let's do that. So this is obviously the third computer project, and we are looking for laminar, steady, incompressible flow with no pressure gradient. And if you go back in our equations of motion, you'll see that there's two equations, right? There's continuity and momentum. And this is obviously an x-momentum equation. And you might say that these are steady flows. They're laminar. So I dropped the bars. I think if you take the Rand's equations and you say that it's non-turbulent, so the Reynolds stress would be 0, the pressure gradient term goes to 0, and then we would say, oh, well, we got Reynolds averaging, we got bars and primes. The primes are 0, so then I'll just drop the bars in the notation. You can count in your results too. So that's why it's like this. Looking at variables, we got u, component of velocity in the x direction in a boundary layer. V is the cross-stream direction away from the wall. Just as a reminder, there's our wall. This is u, and this is v. This term nu is your viscosity, which we'll be setting to just sort of standard conditions. And these are the boundary layer form of the equations, which we went in and found the compressible form in our second module on equations of motion. So really solving the incompressible boundary layer equations with no pressure gradient for laminar flow. And then you say, okay, well, I got my PDEs that govern my system, and I want to find u and v in the flow. I probably need some boundary conditions, like all good PDEs. Well, not all have them, but in this case, it's a boundary condition problem, and we're going to try and create a marching problem for subsonic flow. And you'll note this is like an elliptic system of equations. And so we can save immense computational expense by trying to solve this with a marching problem. A more general way, like a general CFD solver today, would solve it like how? With just a general solver where you got some, I don't know, there's probably more advanced methods like simple or piezo or like more general solvers that can handle non-marching problem. So boundary conditions. There's sort of, we would have like a domain like this, and this is the x direction, and this is the y direction. And so this might be like 0, 0, where we start. And so this is really the x-axis, and this is like a y-axis on the axis. And we would need a wall condition. So we'll enforce the no-slip condition at the wall. So at the wall, u is 0, and so is v. And if we had like a mass flux through the wall, we would relax that. So that's what this boundary condition is here. Along all x at y0, we have a velocity 0. And of course, all v, the component velocity in the cross-stream direction, is also 0. So that handles this lower boundary. Then you say, well, what about the upper boundary up here? Well, we don't necessarily know what u is. It should be changing. But very, very, very far away from the wall, you might try and impose some kind of condition. And the condition I choose is this one here, where we have partial v partial y will be 0. So that's just the derivative of the velocity in the cross-stream direction will be 0. And that's one you can enforce. And it makes it a little bit harder. Because remember, we don't really know the solution, but we just know that obviously the gradients, velocity in the cross-stream direction should be roughly 0, well outside the boundary layer. And then we also need an initial condition. Now, I'm going to say we're going to try and do this one, which is harder. Some people try and impose a Boussinesq solution as their initial condition, or some hyperbolic tangent, which is pretty close to the actual solution. But we're going to do what's harder and maybe a little more interesting. And with a Crank-Nicolson scheme, we have good stability. We can get away with this. But you're setting basically u at x equals 0, and for all y, we have u infinity, which is this condition here. And the flow goes left to right. So immediately you see there's sort of like a problem that I have u infinity at a grid point located delta y off the wall, perhaps, and at the wall I have 0. And I don't think that's super physical unless you're at like a leading edge of a flat plate mounted in a wind tunnel, which is probably the most common and traditional boundary layer experiment. So we're kind of mimicking that. And if you don't use some of these schemes like Crank-Nicolson, that might be unstable and you can't find convergence. And the other thing is we'll have to let the flow develop quickly downstream from the leading edge of the plate to make meaningful comparisons. Now in my notes, in my computer program, I actually use 34 meters per second. So we're going to set, as an example flow, we're going to have a low speed incompressible flow, 10 meters per second, going left to right. So you know already that at this boundary, well, I just erased it, sorry, that was a mistake. There we go. At this left boundary, we know the solution. So the only place we don't have a solution is, of course, at the right boundary, which is some distance x downstream. And so we want to basically march from left to right in the streamwise direction, just like you did in the x direction of the second computer project. So here I just say advance the momentum equation first via spatial marching in the x direction using Crank-Nicolson and Thomas linear algebra solver, which you developed and should understand from the last programming project. And then once we go down like one grid point, delta x, in the x direction, then we would find v. So this is a kind of a two-step approach. We go from a position in the downstream direction, the x direction, by one grid point using Crank-Nicolson. And then we should know u at the downstream location. And then we use our knowledge of u to find v through the continuity equation. So that's what I wrote here. After finding a new solution for u at, say, the next grid point, we advance the cross-stream velocity component v via the same method using Crank-Nicolson algorithm in 11.20. Alternatively, you could set up a linear algebra solver to solve for v. So I'll show you kind of my code structure when I did that. Now, we have to discretize this momentum equation, which is 11.21. And that should look somewhat similar to the equation from project 2. But let's just look at it individually, each term. And so this is the full discretization of the equation. You'll see now I have little indices I minus 1 and j. So in like a grid, right? So we have this direction, these are i's and j. And say we're at some, this is our domain, and the grid is structured in this case, and we have delta psi and delta eta. So we're in the computational domain. not the physical grid. And let's just say this is location I comma j. Then this would be I plus 1 comma j. This is I comma j plus 1, etc. So when we're doing this, we're really using a 3-point stencil in the y direction and a 2-point stencil in the axial direction. Because we're really marching from I minus 1j to this location. So the first step is, this is a known values of u and v at, say, I minus 1, and we want to find the new values downstream of u and v at I and j from this point. So the whole stencil will be located at these points. And you might say also down here, to make it even more complicated, is the wall. And we wouldn't be able to apply our 6-point stencil at the wall or at the boundary condition far away from the wall, right? Because the stencil would go outside the computational domain. So we'll also have to kind of apply our boundary conditions differently at the wall and the J-max position. So this grid point way out here where the edge of the domain is, this one here, this would be J-max. And the final grid point might be I-max. And we could call the first condition I equals 1. And this is 1 comma 1 in terms of the grid. So you can see, if this is our flow domain, we're going from left to right, we instantly know u equals u infinity and v equals 0 at the I equals 1 and j computational plane, right? So that's our initial condition. We really know all this. It's known. Okay, so looks like people are done copying that mostly. That's good. And I have extra handouts if you need more scrap paper, if you didn't bring enough. So let's look at equation 1121 and discretize it using a Crank-Nicolson scheme in 1122. And so the first term is u partial x. And that I wrote here, this term. So we have u of I minus 1 and j, and u of I minus u minus I minus 1 over delta x. So that's the u term times partial u partial x. And you might say, well, that's a bit strange, but this is a common discretization. And you see, in this notation, I know the solution at I minus 1. And I'm looking for the solution at I. Right? Okay, now the second term, that's v partial u partial y. So here's my v of I minus 1. I already know that at location j, times 1/2 of partial eta partial y times u of I j plus 1 minus u of I j minus 1 over 2 delta eta. Now you see, I've done something here because this is obviously an x and y, which is the physical plane, and I'm doing a transformation of my grid, which I'll explain more later in this class. But you can see this term here, this is still what? This is just a partial derivative, partial u partial eta essentially, at j plus 1 and j minus 1. So this is at the unknown location because I'm at I. So where would that be in my grid? That would be, if I'm writing in red, at this location and this location. That's the unknown locations. And I average it with the known locations at I minus 1 and j plus 1 and j minus 1. So that's what you see in this second term here. This is known, right? And this partial eta partial y business, this is the grid transformation, which you'll get some insight into a little bit more, and why we're doing the grid transformation too. I'll give you a grid point estimate of savings. So that discretizes the whole left-hand side of this equation. And now we do it to the right-hand side. So we have a viscous term, and since we're doing Crank-Nicolson, we're doing the spatial derivatives at the known and unknown previous location of I and I minus 1. So this is a known values, right? So these are known. And these are unknown, because of course we're at I. And you can recognize this operator these are nothing but the second derivative operator itself. But you see there's a little bit of a trick. Since this is a second order derivative, this can't just be written directly on the physical domain, delta y, because we're going to use grid stretching in the radial direction, or cross-stream direction from the wall. So this is a standard operation, and I'll try and explain how we get the partial eta partial y squared and partial 2 eta partial y squared later. And, but this whole term here is equivalent to this one right-hand side term. So it's important to look at that discretization, because if we have a Reynolds stress term, like if we add in a Reynolds stress here for a turbulence model, we'd also have to have a whole nother term of those equations. Now you can look at this equation and say, okay, well, I basically can set up a linear system from it. That's the trick of writing this nonlinear term this way and still get a very accurate solution that corresponds to Boussinesq's solution. Anyway, there's all these coefficients, and we'd also have to think about how to put them in like ax equals b to form a tridiagonal system, and I'll talk about that in a bit too. We can also, once we find u, we can, one way to do it is to solve the continuity equation for partial v partial eta as negative partial u partial x and 1 over partial eta partial y. Y, of course, we can write partial u partial x, where this comes from, plus partial y partial eta times partial v partial eta is 0, right? So that's, I just solved for partial v partial eta, and that's a simple equation to solve. It's closed form for the differential because you know partial u partial x. If you do this step here, step 1, then you can find u of I and u of I minus 1, and then you find and estimate the derivative numerically right here by, say, u of I minus u of I minus 1 all over delta x, and you can estimate that and then solve for partial v partial eta. You know the boundary conditions. It sounds like you have a simple linear system you can set up. Now that's one way to do it, and I'll show you that in a second. Now what about these grid transformations? Now I'm going to let delta x equals delta eta. I'm not going to use any grid stretching in the streamwise direction. I could solve or save some computational resources, but let's keep it simple for now and just do grid stretching in the cross-stream direction, which is y. So if you look just as a transformation, I might take each partial derivative, say partial partial y, like here, partial v partial y or partial u partial y, and just say, okay, on a little square. I can write that as partial eta partial y times partial little box v or u partial eta. So this is sort of balanced. And you'll see in this scheme, what I've done really is just replace the partial derivatives of y with these types of little expansions. And when you look at this, well, you say, well, I don't really know what partial v or partial u partial y is. I don't really know what partial u partial eta is. That's because u is unknown. But what I do know is the little transformation right here, partial eta partial y, right? And you can calculate that. Why? Well, I already know what my grid points are in physical spaces. That's my computational domain. Like as a CFD user, perhaps, that's what I create with my grid generation tool. Now, if it's a structured grid, then the CFD solver will load up that grid, and it'll create and find numerically what you call your grid metrics. And so let's look at this term partial eta partial y. So eta are the coordinates of my structured grid. And I want to transform my equations through the grid metrics from my computational, or excuse me, my physical grid into a structured with delta x, delta psi and delta eta onto a structured grid. And this just lets me apply my finite differencing scheme uniformly on my grid. I don't have to do any of these transforms like on the fly. So I can calculate this because I know my y coordinates, I know my eta coordinates. So to draw that, let's just say, well, here's my wall, and this is the y direction, and then here's my wall again, and this is the eta direction. And I want to find partial eta, partial y. Now you don't have to do it this way. You could also find partial y, partial eta, and but we're just going to select this one. Now, in our previous project, we just had a constant delta y. And in a turbulent boundary layer or boundary layer flow, most of the flow gradients, and according to boundary layer theory, all the interesting things are happening very, very close to the wall, and most of the flow field is just uniform or have very little change. And I only have so much computer power, even today, and that means I want to put most of my grid points near the wall. So if my solution is in this domain, this is our domain, our world, and I might put grid points like this. And so this is maybe the wall, so we'll just say j equals 1, 2, 3, 4, 5. And you can see that this distance from the wall to the first grid point, that's some delta y1. And the next one is like, say, delta y2, etc. But the problem is now, because I've distributed my grid points in an intelligent way, I've created a major problem myself, that I can't just apply the same finite difference stencil in the y direction, because I don't have constant delta y, it changes. So say I was finding a second order derivative, I would have to have some variable delta y. And you can do that. You can actually find finite difference expressions for variable grid point spacing. But you'd have to do that for every grid point on your grid. And it's not very general. So the idea here is to transform this through this term into a grid where I have constant spacing. And I might as well set that equal to 1. You can really do whatever you want, but life is easier if you just let the spacing be unity, because that way in your code you don't have to put anything in for delta eta. It's always just 1. So this line here is still j equals 1, j equals 2, 3, 4, 5, etc. And so this way I can apply my finite differences uniformly on a grid. I don't have to find like specific metrics, and it can save me a lot of time. So that's how we've transformed these particular equations into transformed equations. And we'll talk, and that means, of course, coding up your coefficients in the matrix is a little bit more work, but then you'll save a lot of computer power. I'll give you estimates of that in a little bit. Okay, so that's where that's coming from. Anyway, you can also find all these other terms, and I'll show you that on the scrap paper in a second. And I say, well, we're going to let delta eta equals 1, and I'll say we're going to also let psi equals x. And that means I'm not doing any transformation in the x direction. So if I have delta x in my physical grid, I have delta x in the computational grid. Now, if you look at nice CFD solvers using structured grids and finite differencing, they often have grid structuring in the x direction. In fact, they might have just a general airfoil, just to give you an idea of what a more complicated situation is like. You have your airfoil, and I have my grid wrapped around it. And there's my grid. And so this is the harder case, right? Because you can try and find transformations from what we would call a C grid and unwrap this into a nice square computational grid. Same thing. This is x, this is psi. So what we're doing is a bit simpler because we're restricting our basically lines, our grid point lines, to be orthogonal to the wall and parallel to the wall only. You don't have any nice general curvilinear grid transformation, which would be way more complicated. But I think the first time you code something like this, if you haven't yet, it's better to do this way. Now you say, okay, well, we have some choices. We can choose things like, what is the distance from the wall to the first grid point? We want to make that small, and we want to be able to control it. And then you say, well, how do I distribute the grid points? And there's basically infinite choices. Most of them are bad. But we're going to choose one of the simplest ways. How do we distribute our grid points from the wall outward? And I'll propose this simple algorithm. So I'll distribute the grid points in the physical domain. That is, where are y locations? to resolve a boundary layer or turbulent boundary layer this way. And so here we have the grid point yj, which is the y line. So if j equals 1, we're at the first line. We'll have a factor h, which is the distance from the wall to the first grid point. So here's our wall. Here's our first line. And there's our h value, h1. And then we'll have some factor k, sup j minus 1 over k minus 1. And for every one of these lines, we can get a value of, say, y1, et cetera, y2, all the way up from the wall. And so this is a simple way to just distribute the grid points. And I've basically, for this flow, I've given you, I've chosen for you. And I said the distance from the wall to the first grid point will be 0.0001 meters to have a nice resolved flow. And then I've also said I would prefer that you would have, like just for a solution, you'll have to check for grid independence that you would have 301 grid points in the y direction. And I think you'll find that if you have maybe 100 points or even less, you'll still get away with really good solutions. So 300 will be overkill, but your full computational domain size will be about 300 times the number of spacings in the x direction. And I'll let you decide what delta x would have to be, because that's also a choice, but at least it's a constant. So you probably want to keep decreasing delta x to march downstream until your solution is also, numerically independent of the grid. So anyway, if you program all this and do it, I would like you to show the typical things in just a PDF, just like before. Quick description of the problem, the equations, which I've given you. You might have to tell me a little bit how you form A and B, which I'll talk more in a bit. Your numerical solution approach, I've given that to you. When I say proof, I don't mean like mathematical, I just mean do a grid independent study. Like say I double the number of grid points. I take delta x and delta y, or delta eta in this case, divide by 2, or just double the number of grid points in the x and y directions. Do I get the same solutions? If the answer is no, then, well, you're not really grid independent, are you? And just a quick discussion of the solution. So you've done this rather well for the first assignment, so I'm sure it's fine. And I look for these plots. So one plot is an outer plot of y versus y max, right? So I'm not looking for eta. And u over u infinity. So that's non-dimensional. And that's at x equals 0. So what does that mean? That's just a plot of your initial condition. And that just proves to you that you're running the right case and your code's working, I guess. And then we say, okay, what happens at 10 meters? X equals 10 meters, the same plot. So you'll have one plot, and I'll show you what mine look like briefly so you know what your solutions look like. You should have 1 of y over y max versus u over infinity at 10 meters. So I'm asking you to march 10 meters down the plate. That's really long, especially for a low-speed creeping flow. And then I ask you to do, it's not really a turbulent flow, but I just call it inner coordinates anyway. I'll just say y over eta, which is your transform variable, and u over u infinity and log-log plot. So we can't really technically get away with truly u plus y plus because it's not really a turbulent flow. So I think it's kind of informal to call it inner coordinates. So I think it's okay. And here's how I would like you to, this is not how eta, mind you, is defined up here, but this is just how I would like eta to be written. So I guess we could call this a different variable. How about we call it like, I don't know, give me a Greek value. Omega? Okay. There you go. I didn't want you to confuse it with the eta coordinate. And also at x equals 10 meters, I want you to calculate the most typical boundary layer parameters, the boundary layer thickness, displacement thickness, and momentum thickness. And I'll show you my algorithm for calculating, because there's actually different numerical implementations for finding these parameters, and they can lead to a bit different results, which is confusing. And I print out of the code. So that's the big part of the assignment. So let's look at, before we get into how I would write the computer program, I'd like to show you some of my results. There we are. And you can see my momentum thickness at 10 meters was 0.000966105 meters. Your result might vary, but you should probably be hitting those numbers. Now let's look at some of the plots. Here's numerical solution outer coordinates at x equals 10. There's u over u infinity. This is y over delta. Delta is 0.99 u infinity, where that y location is. So this is your boundary layer edge at x equals 10 meters, and you can see this value is 1, 1. And I did not plot the Boussinesq solution on top of that, and that's not something I asked you to do, but if you want even better validation and compare what we would consider an analytical solution, which only has a numerical solution because it's a nonlinear third order ODE, you can look for this and compare it directly. And you see it has kind of just a laminar shape. And that's why some people have their initial condition, at the plate leading edge is something like a hyperbolic tangent type function. It's not exact, but it's close. And then I plotted eta versus u infinity as a log-log plot. And I like this plot better because it can show me a little bit better variation. But you can see in this case, here's my boundary layer edge. So what's interesting here is, remember, most of my grid points are located in this region, because that's where my highest gradient is. And if I go to a turbulent flow, this will be even more pronounced. And so that's all set up if you do this correctly for the fourth project. And I like this coordinate system because by doing a log plot, they're becoming more evenly distributed. And you can see I have a large decade of where the boundary layer is. Okay, those are kind of what your solution should look like. Now let me talk to you, if you would, about how I kind of wrote a program to do this. And I think some of you will benefit, and some of you are doing pretty good jobs at writing your programs. Okay, let me find my notes on this. Remember, this is a 2D, steady, incompressible solver for laminar flow. And I want to make a few notes. So one of them is I had this equation for distributing y, and that was yj equals h1 times kj minus 1 all over k minus 1. And this goes up to j max, right? And k is bounded. And so k is really my way of, it's a factor which I'm using to distribute the points. Oh, did I do that wrong? I think actually k is not bounded like that, because I set k, ratio of 2 consecutive steps. So I'm sorry, k should be greater than 1. I didn't think that was right. And I set k equals 1.04 is what I recommended. So that means you're getting about a ratio of 0.04 increase. So if my distance from the wall to the first grid point is 1, the distance from the first grid point to the second grid point would be 1.04, etc. So then you can say, well, the total number of points generated by this, we might call that j, and that would be natural log of 1 plus k minus 1 times y infinity over h1 times all over the natural log of k. So here, y infinity is the this distance in your domain. That's the distance from the wall 0 to your largest grid point outside. So you can estimate your grid points without running the algorithm, which is nice. And then you can also get total grid values and estimates. Alex?
So is y infinity the physical distance or the number of grid points?
Y infinity here is the physical distance.
Okay, because I think on the first page you put the number of grid points in the market.
Oh, did I do that? Yeah, you're right. I am very sorry. Thanks, Alex.
Okay, so there's grid points.
Yep, so this is 301 in the homework case. Sorry about that. And, okay. I guess that's good because H1's in meters and Y infinity would be in meters. or grid points. I'm gonna have to go back and look at how I found this formula because I wrote it down or didn't record my notes. But I think it works because I put it in my code and it was giving me the right values when I checked the generation. Okay, good catch. Other little points and things I'm checking on to make sure before I get into my code review. Oh yeah, so then these conditions at the wall. So let's see here, let's just say that we have, just as a test, we have y infinity equals 100. And we'll let h1 be 0.001 and k equals 1.04. And I run this algorithm. Then my ratio, y infinity over h1 will be about 100,000. And then we'll find the number of grid points from the algorithm is, of course, 100 by definition, even if we run the algorithm. And so that's nice. Now what happens as a second case? We have no grid stretching. So we'll do the same thing, but now k equals 1. Well, what happens is you'll generate, with the same parameters, 100,000 points. So we have basically the same grid point spacing from the wall to the first grid point, and we've kept a constant delta y, and you'll generate 100,000 points for the same computational domain thickness relative to grid stretching with only 1.04. So you see the difference in the computational size is 100 with grid stretching or 100,000 without to resolve the boundary layer, the same grid point spacing near the wall. So this is really the motivational factor and memory saving we get in computational too, by using the grid stretching approach. So hopefully that's just a little example. But with your code, it's kind of fun to experiment. You can go in there and change k to say like 1.5 or 2, and you'll obviously get very aggressive stretching, but your code should still work, and you can also see how that affects your solution. Or you can set k to 1 and watch your code come to a crawl. Let's look back at this discretization and just a few ones to recall, like say we had partial u, partial y at I comma j. So this was the unstretched or one, so we might have u of I, u of j, oh dear, sorry. U of j plus 1 minus u of I, j minus 1 all over 2 delta y. So that was the standard one. And second order would be partial tu, partial y squared at I comma j. And that would be u of I, j plus 1 minus 2 ij plus u of I, j minus 1. And that would be delta y squared. Okay. So these are the standard ones, but they're in physical coordinates. And we might want to think of a way to transform them. So once again, partial y equals partial eta, partial y, partial eta. So we would basically take this form and put it in here to get the transformed one, which was discretized earlier. So for a general first order derivative, let's just look what that looks like. Partial phi, partial y. So phi could be u or v equals partial psi, partial y, partial phi, partial psi, plus eta y, partial phi, partial eta. So that's the general definition. Now, psi and y are not changing, right, in the grid. That's should go to 0. And so we're really left with the second term, which is partial eta, partial y, partial phi, partial eta. So this is the general form of just a partial derivative with respect to y. And so that would reduce to partial phi, partial y equals eta y. That's partial eta, partial y times partial phi partial eta. Now for the second order derivatives, it gets way more complicated. So let's write that one out. It'd be partial 2 phi partial y squared equals psi y squared, partial 2 phi partial psi squared plus 2 psi y eta y partial 2 phi partial eta squared plus eta y squared partial 2 phi partial eta squared plus psi y partial phi partial eta plus eta y partial phi partial eta. So this is just general 2D transform second order derivative in the y direction. So this is what you would program for a general two-dimensional solver if you wanted to find this derivative, which would be your viscous terminal momentum. But we're applying it to boundary layer flows. And we would reduce this to partial 2 phi partial y squared equals partial eta partial y squared partial 2 phi partial eta squared plus partial 2 eta partial y squared times partial phi partial eta. Now, when we were looking at the Crank-Nicolson discretization of the viscous term, you saw 4 terms on the right-hand side of momentum, and 2 of them are at the unknown location I, and 2 of them are at the known location I minus 1. So this is where the discretized form of the momentum equation, viscous term, is really coming from. So you can go through here and see some of these are 0. For example, partial psi partial y squared is obviously 0 if you look at the grid. The grid points psi or x are not changing with y. They're always the same. Make sense? Now, if you want to know more, because that's not really the scope of this class of transforms, you can go on Google or Google Scholar and look up grid metrics or Jacobians. And this is all about transforming your computational grids to, or physical grids to computational grids. And this is probably one of the things that is hard to get your head wrapped around. And it's one of the nice things about like finite volume schemes that you're thinking about fluxes and surface areas. This is way less intuitive, or finite element methods. But then you have your own transform problems. Okay, so we're going to try and take all this information and put it in a general program. This is my strategy. Of course, in programs, we always want to initialize them, right? And if you're in Fortran, you probably have to define all your variables, implicit one. In Python, you get all the modules and go from there. So the variables I initialize, I have one called U, I, and F, and I would write 10, right, for meters per second. So that's my boundary condition. I probably want that. And I wanted rho, I, and F, and I set that 1.204118 kilograms per meter cubed. So I'm going to have density. I had to have viscosity, so I call that nu INF. And I put that as 1.4146 times 10 to the negative fifth. That's meters squared per second. And I needed another variable to control is the number of grid points. And I set that to 301. And just for a test, I had delta x, and I put it 0.01 meters. That's a large step size to get away from the initial condition. If I had a developed profile, I could take much larger step sizes. In fact, the farther I go downstream in this boundary layer, I could take larger and larger steps, delta x. So we are having a computational cost of laziness of not transforming our equations in the x direction. Other things, you might say, well, how far downstream do I want to go? I did it this way. I said mx max equals 1,000 dx as a test case. Why? Because that would give me about 10 meters downstream. And that would go into my loop to have like 1,000 steps. Now I also had to say, okay, well, what are my ranges of J min and J max? I put that as 0, and J max equals, say, number of grid points minus 1, because I like to have 0 at the wall, and J max minus 1 being my largest index in the y direction. So that's just my own style and convenience. And I also set all these coefficients like h and k and all that. So etc. Any other coefficients you need, because then I need to generate the grid. Then in Python, if you use Python or Fortran, you've got to go further and define your variables and set them to 0. So that's what I did here. I set, say, my initial conditions, you know, like u equals uinf, v equals 0. And I also said u of, and I use m instead of I, because I like to use m as a counting integer, say m minus 1 equals u, and v of m minus 1 is v. And so here, I just let m be the station I'm at. So m is just the index location in the x direction. So you see, to start the solver, I really need to know something, right? And since I have a 2-point solver in the x direction, I'll just say I know the initial condition. Now what happens if I wanted to use a higher order method? Say I have a 3-point stencil in the axial direction of the flow. What would I have to do? Well, I would probably have to try and also set the initial condition to be at multiple points, which is kind of a strange thing to do. So anyway, after I do all that, I would have to create my computational grid. And so I would just say for, I don't know, j from 0 to j max, basically. I would have y values of j equals something like h1 times k to the j minus 1 all over k minus 1, something like that. And immediately I would distribute my grid. And I could write that, plot that to a file or a figure and check that I've done it correctly. And that's probably a good thing to check, because if you're not putting your grid points and distributing them in a reasonable way, then nothing else you do matters. I've already set my initial conditions, and in my own notes, I transform my project 2 code to my project 3 code. And so I commented out my initial conditions previously, which was the sine wave, and set it to u infinity and v equals 0. I also set, once again, v minus 1 to um, or u m minus 1 to um, and v minus 1 to vm. The next thing I did is I echo my input. So I write everything in memory to either files or the screen. And by doing that, I know what's in the computer memory and what's going to go into the program. And for larger programs, sometimes I didn't do that. And I remember spending a few weeks of my life as a researcher trying to debug a problem where I had the wrong initial condition. And so there's really nothing wrong with my code. It was just a user error. And I didn't think to check that I input the right initial condition. That's 3 weeks of my career. So don't make that mistake. So we've done all this. We created the physical grid, but now we probably need to calculate the grid metrics, the transformation from the physical domain to the computational one. So the next step is to calculate grid metrics. Okay, so how do we do that? Well, we're going to have to loop over J. And we only need to do this once, right? Because our grid isn't changing as we march downstream, at least the distribution of grid points in the y direction. And I'm going to write, I need to find partial eta, partial y. That's one I need to find. And let's do that one first. And I call that p eta, partial y. So P partial eta partial y at j. And here's the algorithm I used. I wrote 2 times delta eta, which is going to be unity always, all over y value of j plus 1 minus y value of j minus 1. So I'm trying to estimate partial eta partial y, and I've done that by applying a finite difference technique against my grids. So what does that mean? In the denominator here, I have a delta y. So I've just estimated delta y by using the grid points in J and put that in the denominator. And I estimated the numerator, which is basically a delta eta, as 2 times unity. So if you flip this over, it's just like getting partial y partial eta, which fits the exact definition of a first order derivative. Okay, anybody have any questions about that? Super simple when you have a 2D structured grid like this. Okay, the next step is I'm also going to need partial 2 eta, partial y squared. And that's the same type of algorithm where I have like a delta eta squared in the numerator, and then the denominator I'll have what? Y val of j plus 1 minus 2 y val j plus y val at j minus 1, which is the exact definition of the second order derivative, right? J plus 1 minus 2 y val j plus y val j minus 1. And you can construct your grid metrics for any other operation on eta and y this way, and loop over them from all j equals 1 to j max minus 1. Now you might also say, well, what about my grid metrics at the boundaries? And well, you certainly don't need one at the wall, but you might need one at the outer part of the layer. So after this loop, I'll have to have another term where I might say partial 2 eta partial y squared at j max, because it's a boundary, might be partial 2 eta partial y squared at j max minus 1. And so that's not exact. What I should have done, technically, is evaluate a partial derivative using a one-sided finite difference stencil, not a centered stencil. And but the grid stretching is not too important out there anyway, because I'm going to enforce the boundary through the linear algebra solver. So this is cutting a corner, but you can program that if you want. So now I've gotten my grid metrics. You also need to know the eta vals. So I would find the eta vals. This is just eta, of course. And I would loop over j and would say eta of j equals j times delta eta. And this might be silly to you, but this gives me control over what delta eta is, because I might set it to 0.1 or 2 or just leave it as unity. But this is nothing saying then eta of j equals 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. Because it's a structured grid with uniform spacing. Okay, I've done that. I've already set my initial conditions. I've echoed my data. I might echo this data too for these things. And now I'm ready to go into the main solver algorithm. And this is where it gets more complicated. So then this is the solver. So this is just like the preprocessor. And we're going to have a shorter class today, so instead of a break, let's just finish the solver, okay? You can leave a little early. So my solver is really a two-step solver. I'm going to solve the momentum equation, and I've discretized it, but I'm going to send it through coefficient matrix A and set a right-hand side B and enforce boundary conditions and use a tridiagonal solver to solve it. I'm going to use that solution to find U at I, and then what? I'm going to solve for V. And then I'll have V at location M in my code, or I in terms of the grid. So I put my whole solver in a while loop. which is a little bit redundant because I've already set a number of locations. You can do it either way. I said while x coordinate is less than, say, x max. So I would go in there and say x max equals 10 meters, for instance, and I would update x core before this is x core equals 0, right? Because I'm at 0 meters. And the first thing I need to do is construct two things, A and B, for AU equals B, right? So this is going to be a little crazy. The first thing I do is I set A equals 0. And I just get rid of the whole matrix, and you might be storing it as 3 bands, which would be smart, because your number of grid points is 300, right? So you wouldn't want a 300 by 300 matrix. Just store 3 rows. So the first thing is to maybe look at the upper band. And how would I identify what goes into the upper band of A? Well, go back and look at your discretized equations, and sometimes you might even have to draw out what A looks like on paper. So this is what I did. I said for J in range, so I did mine in Python, from J min plus 1 to J max. So I'm looping over a range of J's, but not at J0. And I say basically a matrix of 1 comma J equals a matrix of 1 comma J plus U of M minus 1 at J divided by delta X. So that corresponds to one coefficient of the momentum equation. And you can see this is a known coefficient because I'm at U of M minus 1. So this is really the coefficient. And I maybe don't know in advance how to construct A in like a truly closed form way. I wrote it so that I can always modify the code later by changing my discretization. So I set A to 0, and I just add or subtract to A with coefficients that I know, because it's an A, right? So coefficients, so this is being multiplied by, of course, a U value. So that's just one value. Now let's just do another one. This is a center band. Okay. So then there's another one in the center band, probably with viscosity, and be A times 1 comma J in the matrix equals A of 1 comma J plus nu infinity times 1/2 times partial eta partial y at J squared times 2 over delta eta squared. So if you look at your equations, this is now center coefficient in A of the momentum equation. So those are just in the range between the wall and the outer boundary, and for the center of A. So you'll have to go back and look at these two coefficients in the discretized momentum equation. And that's just for the center of A for the momentum equation, right? Now we say, well, what about the boundaries? Well, for the one boundary, let's just say A of 1 comma 0, right? Because J is 0 in this center band. I just say equals 1. And so that means I'll have to set the right-hand side to something, because I have like 1 times U at the wall equals B. And so B might be what? Something like 0 in the B vector, which we haven't discussed yet. And I need one more. Well, I need what the coefficient of A at J max would be, equals 1. So then I'll have 1 times, say, whatever U is, it's an unknown, equals U infinity in the B vector. Okay, so I'm enforcing my boundaries explicitly by altering the coefficients and overriding them in the A matrix. Good strategy. And that's what they do in large direct linear algebra solvers usually. Okay, so that's basically the center band of A. And now I would have to do the same thing for the upper band, which I call A of 0 comma J. So 0 is upper for me. And I would do a lower band. And I have A of, say, 2 of j. So A of 1 is center, A0 is upper, and A2 is lower. And that's, I did that because of just the way Python talks about linear algebra. And once again, I would have to go in and look at my coefficients and put them in, and for my discretized equation. Now I gave you 2 examples. Do you want me to give you another for, say, an upper or lower bound? Or I'll let you handle it? Shake your heads no or nod yes. Just depends. Okay, I'm getting mostly no's. Looks like you know how to do that. That's great. Okay, so I've done A. Now I want to construct B. Right. And thankfully B is a vector, so I say B equals 0 again. And I have my boundary condition enforcement. So B at, say, 0 equals 0, like I mentioned before. And B of j max, something like that, equals what? U infinity. So I've enforced my boundary conditions, which is nice. But remember, I'm letting V vary. So V can be positive at the boundary. It should be positive if you do this correctly. And now I need to find out what's in the middle. Well, since it's a vector, I can just loop over j equals, say, 2 to j max minus 1. And you can see the B coefficients are numerous. For example, I would have u minus 1 at j times u of minus 1 at j over delta x. And I would have terms from the V term in the momentum equation. And then I would have multiple. In fact, I count 2. I've written 4 lines. I have another 2 terms involving the viscosity. So that all has to go in the B vector because to form your full set of equations. So for example, I'll give you one. I would say B equals B at j. This is also at j. Plus um minus 1 of j times u of m minus 1 of j all over delta x. So there's one example. And the next term would be, let's just write it out, give you another one, v of m minus 1 at j times a half times partial eta partial y, all times u of m minus 1 at j plus 1 minus u of m minus 1 at j minus 1 all over 2 delta eta. So you can see that comes indeed from one of the the V term. The next 2 terms you might have are, let's just write one out just so you can complete it. There'll be another u infinity term. And times 1/2 times partial eta partial y at j, and that would be squared, times partial y of 2 of the term u at I minus 1, or m minus 1, sorry. And you'll have to call your second order derivative function, which you wrote in your previous programming assignment. And you'll have a similar term like that. Okay, so then you found A and B. Now you solve it through your standard tridiagonal system. Okay, and then at the end of all this, after you loop over and you find your solver, then you have u at m, which is new. Okay, so that's the first step. The second step is you do the exact same thing, but for the continuity equation to find v. Now, you just say a equals 0, b equals 0, and vm is unknown. Use the same algorithm with continuity equation and set up A and B. Tridiagonal system for Vm. And you'll have to go through and look at the discretization and continuity equation to do that. That's no problem. So now you know Vm and Um, which is great. And we'll set U of M minus 1 equals Um, and Vm minus 1 equals Vm. And then you repeat your loop. And then you're done, because you've looped until a particular x location is found. And so now you found your, say, profile at 10 meters or 5 meters or however far you marched, and that's wonderful. But what do you do with the data? Well, we want to find something useful, and it might be something like boundary layer thickness, etc. So we want to calculate our boundary layer thickness, our displacement thickness, and momentum thickness. So I say, for example, let's do displacement thickness. I'll just write dt for displacement thickness at 0. And then I would say, well, I need to correct what it is near the wall. So I'll say 1 minus 0, which is 1 times y value at 1 minus y value at 0, all times 1/2. So that gives me the wall estimate, because I'm doing a numerical integral. And then I loop from j equals 1 to, say, j max minus 1. And I would say the displacement thickness, something like 1 minus u of j over u infinity times y value of j plus 1 minus y value of j, 1 times 1/2. Oh, that's minus 1. So that's dt plus 1 minus uj over u infinity times y value of j plus 1 minus y value of j minus 1 all over 2. So what does this algorithm look like? It's looking like I'm doing an integral from 0 to infinity of 1 minus uj over u infinity times something like dy. Boundary layer thickness. You can do this a formal way or just estimate where 0.99 u infinity incurs. And you use linear interpolation. And then momentum thickness is found the same way, just different algorithm. And what that be? Let's just write that as theta for kicks and write it as something like an integral from 0 to infinity. You know it's going to involve dy, and it's going to be something like uj over u infinity for incompressible flow times 1 minus uj over u infinity. So you see it's very much like displacement thickness, but I have this extra term here. And when you do that, you can discretize it in the same way. You're going to put it in the same loop. That would be like momentum thickness plus uj over u infinity times 1 minus uj over u infinity times the delta y. And I replace this with the same algorithm up here. Y value of j plus 1 minus y value of j minus 1 times 1/2. Right there. Does it make sense? So I've just created some loops over j, and using a basic, area under the curve concept to evaluate my integrals numerically. It's pretty low order, but when you have a lot of grid points, it's not going to matter. And that's really the end of the code. So at the end of all that, I spit out all my plots and write my report, and I'm done. So that's the big overarching strategy for this. And I think I made the project 3 due in about a month, March 22nd. So gives you a lot of time. And this is the hardest project, because you'll see in project 4, we're going to just go in and add one more discretized terms to the A matrix for the turbulence model, and add the eddy viscosity to the laminar viscosity, and be done. So that should take you, an hour. The problem is you got to run the code and compare it to the composite profile, which takes a little time, but I think you'll find it instructive. So, okay, so with all that, is there any questions about the third project, the equations? No? Everybody's happy? Okay, great. Well, thanks for your time today, and we'll see you in 1 week.